Here's our problem for today. I want to find the critical points of this function, this cubic function, and I want to classify each of the critical points as a local maximum, a local minimum, or neither of those. And I also want to find the inflection points of this function. Now, there are certain things that we know just based on the degree and the leading coefficient of this function. So f of x is x cubed minus 9x squared plus 27x minus 18. So here are the things that we know just based on the leading coefficient. So since it's a third degree polynomial, that means it can make at most 2 turns, or it could make 0 turns. And since the leading coefficient is positive, I know that we go to infinity as x goes to infinity. So just based on the fact that we have this x cubed, I know the graph either goes up, down, and then up again with 2 turns, or we could have a graph that has 0 turns. 0 turns could mean that the graph goes up, flattens out, and then continues to increase. 0 turns with a flat point. Or we could make 0 turns without a flat point. The number of turns will be, we'll find the number of turns based on the derivative, f prime. So notice that f prime is going to be quadratic. So f prime of x is quadratic. So we'll need f prime is 3x squared minus 18x plus 27. F prime is quadratic, and that's going to tell us the number of turns. And that makes sense. The quadratic can either have 2 real zeros, 2 distinct real zeros, 1 repeated real zero, or no real zeros, 2 complex zeros. So a quadratic with real coefficients will either have 2 real zeros, distinct, one repeated real zero, or 2 complex conjugate zeros. This is what we know about quadratic functions. We got to have 2 zeros, so it's either 2 distinct real zeros, 1 repeated real zero, or 2 zeros that are complex conjugates. And those correspond to our 3 possibilities for the number of turns. We'll have 2 turns if we have 2 real zeros. Distinct real zeros. We'll have no turns with a flat point if there's 1 repeated real zero. And we'll have no turns, that is without a flat point, so no flat points, if the derivative has no real solutions. And that would mean complex solutions. So f can have 2 turns, 0 turns with a flat point, or 0 turns with no flat point. And that would mean that f prime has either 2 distinct real zeros, 1 repeated real zero, or complex zeros. As far as inflection points go, based on what the graph needs to look like, Notice that in each case, we always have an inflection point. In all three cases, f has an inflection point. No matter how we draw the graph of f to fit this description, either with 2 zeros, 2 turns, no turns and a flat point, or no turns and no flat point, to draw a cubic graph, we've got to have an inflection point somewhere. That makes sense because the inflection points will happen at the zeros of the second derivative. And if we look at the second derivative, f double prime of x is going to be 6x minus 18. This will always have exactly one solution. In all cases, f double prime has one real zero. Because f has to have an inflection point. At some point, the function has to change concavity. And based on the shape of the graph, we know it has to change from concave down to concave up. And we can even see where that happens. 6x minus 18 is equal to 0, x equals 3. That's where our inflection point is going to be. Since our second derivative is a line and with a positive slope, f double prime is negative before 3 and positive after 3. So this is all information that we have just based on that leading coefficient. It's got to be one of these three cases for a cubic polynomial graph. We know we can make 2 turns, 0 turns with a flat point, or 0 turns with no flat point. But we also know there's definitely going to be an inflection point, and we know where it is. Okay, based on the shape of the graph, we have to have an inflection point. And we want to think about what's going on in the first derivative and what's going on in the second derivative and why we know all these things. We want to do this because think about the shape of the graph, because we don't just want to just blindly walk into the function and hope that all our calculations are correct. Let's know what things we might be looking for so that we won't be surprised when we find it. Now let's go through and find where all these points are. To find the critical points, we want to find the first derivative and set it equal to 0. So we take f prime. We want to solve f prime of x equals 0 for the critical points. So f prime is 3x squared minus 18x plus 27 equals 0. We can divide everything by 3. Drop this down to x squared minus 6x plus 9 equals 0. And now we can see what situation we are in. X squared minus 6x plus 9 is x minus 3 squared. And so x equals 3 with multiplicity 2. We have a repeated real 0. So that tells us that the function goes flat at 3. But when we plug 3 into the second derivative, we can see there's no concavity at 3. So that doesn't work. So we can also check the sign of the derivative before 3 and after 3. But since the first derivative is a parabola, if the first derivative is equal to 0 at 3, and that's the only point where it's equal to 0, we know the first derivative is going to be positive before and positive after. So the function is increasing before and increasing after. So if we look at the graph of f prime, we've got a parabola, and since there's only one real zero, the vertex is the x-intercept. This means that before 3, so f prime is positive as long as x is not 3. Therefore, f is increasing when x is not 3. So now we know what shape this graph has. It makes 0 turns, but it does go flat when x is equal to 3. We weren't able to check the concavity because the function does not have any concavity when x is equal to 3, because the second derivative is equal to 0. But f has a critical point at 3, and it is neither a local maximum nor a local minimum. And it is neither a local maximum nor a local minimum. We know what the graph looks like now. It makes no turns. It's increasing everywhere but 3. So we know we're looking at this middle picture. We also know there's an inflection point, and we know where that inflection point is going to be, even if we didn't already solve here. But we solve f double prime of x equals 0 for the possible inflection points. We know that the second derivative is going to be 6x minus 18. Set that equal to 0, and we get x equals 3. And now we see why we weren't getting a local minimum or a local maximum. Or actually, well, because we had a cubic polynomial. So f double prime is negative before 3 and positive after 3. So if I look at the graph of f double prime, we have an x-intercept at 3, 0. F double prime is negative when x is less than 3. Therefore, f is concave down before 3. And f double prime is positive when x is greater than 3. Therefore, f is concave up when x is greater than 3. Therefore, f is changing concavity at 3. So f has an inflection point at 3. Because the function is changing concavity. So we have a critical point. And it is neither a local maximum nor a local minimum.
Professor Lich, I have a question, please, Professor Lich.
Uh-huh.
On the top, it said solve f prime of x equals 0 for critical points. And then on the right, you have the quadratic.
Yeah.
F prime of x, 3,
Yes.
0. So what it means, so the reason it go up because the 3, they have the multiplicity with the x squared. The coefficient, leading coefficient is positive. That's why you draw up, correct?
Yeah, the parabola opens up, nothing to do with multiplicity. The parabola opens up because the 3 is positive.
Okay.
The leading coefficient is positive.
Got it.
Not this 3 down here, this 3 up here.
Okay. So the reason it's quadratic because of the multiplicity.
No, the reason it's quadratic is that there's an x squared.
Right.
This is what the degree tells it's quadratic.
Right. And then the bottom you have f prime of 0 when x cannot be 3. What does that mean?
F prime when x is not, f prime is positive whenever x is not 3, because the values of the function f prime are always positive, except when x is equal to 3, because then f prime is equal to 0.
Okay. And then the bottom, then you have the f double prime equals 0 for positive.
F double prime is positive when x is greater than 3. So when x is greater than 3, f double prime is positive. And that means since the second derivative is positive, the function is concave up when x is greater than 3.
If it's less than 0, then it's concave down.
If what's less than 0?
That means it approach to the left, isn't it?
No, you said it, and it doesn't mean anything here. If f double prime is less than 0, then f is concave down.
Okay, I almost get it. Professor, could you please scroll up a little bit to the up a little bit, one more, a little bit. Yes, right here. It said f has the 2 term, and then f prime has 2 distinct real 0. Where that 0 located? Could you please show us on that?
It's not on this graph. Up here, I said f has one of, it looks like one of these 3 graphs. We don't know which one it is yet.
Oh, okay.
So f doesn't have 2 turns. We found out that f only has, or f has 0 turns. But this is just based on the leading term in the polynomial. These are one of the 3 possibilities.
Yes, correct. And then on the bottom, you have f prime has 2 distinct real 0 on that one. Where is that 0 at? Where the 2 distinct real 0 located?
There'll be whatever the values of the maximum and minimum are.
The max and the min.
Because if f prime has a 0, that means the function is flat.
Oh, so it could be either the max and the min. Okay, thanks.
Yeah.
I understand. Thank you.
Let's take a look at another example. Let's suppose that g of x is equal to, let's see, which one did I want? So let's say that g of x is equal to, I'm just going to cheat because I want, let's go with x minus 3 to the 4th power. And then same question. Although they weren't actual questions, they were more like requests. Same 3 problems. I want to find the critical points, classify each one as local minimum, local maximum, or neither. And I want to find the inflection points. So let's think about what this graph looks like, even though we know quite a bit about what this graph looks like. Originally, I was going to give you the multiplied out version of this, x to the fourth, and then a bunch of other terms. Minus, let's see, other stuff. But I want to emphasize what we know just by looking at this graph as x to the fourth. And then there's like a bunch of other terms. Just based on the degree of this polynomial, since the leading coefficient is positive and the degree is even, that means that we can, and since the degree is 4, that means f can have, it could make 3 turns. So it could be that the graph looks like this. So 1, 2, 3 turns. Or the graph could make 1 turn. Now, there's a couple of other things that could happen. So here's a case where it makes 1 turn. Since the ends have to go in the same direction because the degree is even, it makes sense that we should expect an odd number of turns, because an odd number of turns is how we get the ends to go in the same direction. So what this means is that if we look at f prime, when we have 3 turns, those correspond to the zeros of f prime. And if there are 3 turns, that means f prime must have 3 distinct real zeros. We know that f prime is going to be cubic, because if we start with a 4th degree, the derivative is going to be 3rd degree. So we know we have to have 3 zeros. It could be that we have 3 distinct real zeros, and that gives us 3 turns. It could be that we have 2 real zeros where 1 is repeated. So 1 real zero with multiplicity 1 and 1 real zero with multiplicity 2. That would be like a x minus 2 squared times x minus 1. So it could be that we have 3 real zeros, but one of them is repeated. And if that's the case, then we'll have 1 turn and 1 flat point. Oops, 1 extra flat point. It could also mean that f primes being a 3rd degree could have 1 real zero and 2 complex zeros, which mean we'll have 1 turn and no other flat point. Because a cubic polynomial could have 1 real zero and 2 complex zeros. There's a few ways that we could have 1 turn and no other flat points. Maybe there's 1 turn and no inflection points. It could be, though, that we make 1 turn here's a turn, and we actually change concavity later. It might be 1 turn and no inflection points, or 1 turn with an inflection point. No, concave up. Oh, no, sorry. I was saying inflection points. It could be that we have just 1 V-shaped graph, or kind of rounded V, or it could have this extra swerve in it. It's not changing concavity. Wait, it is. Sorry. concave down, and then concave up. So it could be that we have no inflection points. I normally do these in the other order. It's messing me up. Or we have an inflection point, multiple inflection points, actually. But these are the possibilities for a third degree polynomial. We either have 3 distinct real zeros, which would tell us there are 3 terms. It could be we have 1 real zero and with multiplicity 1 and 1 real zero with multiplicity 2. There are 3 real zeros, in which case we'll see 1 turn and 1 flat point, or f prime being a cubic polynomial could have 1 real zero and 2 complex zeros. This means we're going to only make 1 turn and there will be no other flat points. That could be a result of the 1 turn and no inflection points, or 1 turn and 2 inflection points. So we have 0 inflection points. Or here we have 1 turn and there must be 2 because it's concave up, concave down, and then concave up again. So there must be 2 inflection points. Inflection points come from the second derivative. The second derivative is going to be quadratic. Notice in this 3-turn case, we're concave up, concave down, and then concave up again, which means you must have 2 inflection points. If there are 2 inflection points, then the second derivative must have 2 distinct real zeros. Let's take a look at this case. So the second case where we have 1 turn and 1 flat point. So we have concave up, and then it's concave down, and then at that flat point, it changes to concave up again. So here we have 2 inflection points. But in this case, where we only make 1 turn, and there are no other flat points, there are no inflection points. We just go for, it's concave up the whole time. 2 inflection points must be 2 distinct real zeros for f double prime. 2 inflection points in this last case must be 2 distinct real zeros. But if there are no inflection points, let's take a look at this problem. And we have the easier form, the x minus 3 to the 4th. Let's take the derivative, set it equal to 0, and solve and see what we get. Oh, I see what I did now. I put these 2 together and I shouldn't. Let's find out where I messed up. So let's take the first derivative, g prime, 4x minus 3 to the 3rd, set it equal to 0, and solve. We get one solution, x equals 3, and it has multiplicity 3. That's the one that I left off. So there's only 1 real zero, but it counts 3 times because it came from a 3rd degree polynomial. See, this is what happens when you switch the order that you do your cases in. It gets all messed up. Glad these kinds of mistakes are nice and recorded on camera. So we've got 1, 0. G prime has 1, 0, but it has multiplicity of 3. If we look at the graph of 4 times x minus 3 to the third, so this is the kind of cubic graph that goes flat and then keeps going up. So G prime is negative before 3 and positive after 3. So G goes from increasing to increasing. So G goes from decreasing to increasing. So G must have a local minimum at 3. So G prime is negative when x is less than 3. So G is decreasing when x is less than 3. G prime is positive when x is greater than 3. So G is increasing when x is greater than 3. That tells us that G has a local minimum when x equals 3. The critical point is at 3, and it is a local minimum because G changed direction. And we can tell that because G prime changed sign. To find any inflection points, we start by looking at G double prime equals 0. So G double prime is going to be 12 times x minus 3 squared equals 0. So here we get 1 solution and it has multiplicity 2. Because that solution came from a squared factor. So here we see that G is not changing concavity because G double prime does not change sign. So the graph of G double prime, which is quadratic, has a vertex on the x-axis, or the vertex as an x-intercept. So G double prime is positive whenever x is not 3. Therefore, G is concave up when x is not 3. Maybe the more important thing to notice is that G is never concave down. From a task at hand standpoint, G has no inflection points. Going back up to our possible images, what we're looking at is this scenario where there are no inflection points. So this is what's going to happen when we have one real zero, but with multiplicity 3. And we got no other bends in the function because f double prime with the one real zero with multiplicity 3 for g prime came from an x minus 3 to the third. And if there's an x minus 3 to the third in g prime, g double prime will have an x minus 3 squared. So we have g double prime has one real zero with multiplicity 2, which means we're not getting an inflection point. Then the third case was labeled properly before, where we had one real zero plus 2 complex zeros. And so the graph that we're looking at, if we switch over to the Desmos graphing calculator, that's what we see. This is the same as x minus 3 to the 4th. We see down here at the bottom a local minimum at 3, 0. But we see no inflection points. We have a graph that's concave up the whole time. I didn't go with this original formulation because we'd have to solve a cubic polynomial equation, and I wasn't sure that we would recognize it as the cube of x minus 3. But notice that we only have a limited number of possibilities. It's also bugging me that I started calling this f, and these are all g's. And this is all based on the stuff that we were talking about with polynomials. An nth degree polynomial with real coefficients definitely has n zeros, counting multiplicities, and complex zeros always come in conjugate pairs. If a plus bi is a complex zero of a polynomial with real coefficients, then a minus bi is also a zero of that polynomial. So when we're looking at the derivative for the number of terms, a fourth degree polynomial will have a third degree derivative. And that means we have to have 3 zeros. It's either 3 distinct real zeros, 1 zero with multiplicity 1 and 1 with multiplicity 2, 1 real zero with multiplicity 3, or 1 real zero and 2 complex zeros. If the polynomial g prime has real coefficients, there's no way to have 3 complex zeros. We have to have 1 real zero. And that makes sense. If we think about the graph of a cubic function, if the ends are going in opposite directions, at some point that graph has got to cross the x-axis. You can't get from negative to positive continuous in a continuous fashion without being 0 at some point. Any questions? So we can get a lot of information just by knowing about polynomials. We could think about all the things that would happen with a fifth degree polynomial. Let's suppose h of x is a fifth degree polynomial. Let's say with a positive leading coefficient. That tells us that h prime is going to be a fourth degree polynomial. And what are the possibilities for the zeros of a fourth degree polynomial? I could have 4 distinct real zeros. I could have one zero with multiplicity 1 and one real zero with multiplicity 3. I can have 2 real zeros with multiplicity 2. I can have going backwards. I could have 3 real zeros with multiplicity 1, 2 real zeros with multiplicity 2, 2 real zeros with 1 with multiplicity, 2 real zeros with multiplicity 1, and 1 with multiplicity 2, because I just need to have 4. And I could have complex zeros. I could have 4 complex, two conjugate pairs. I could have 2 complex and 2 real. And these 2 real could either be distinct real or 1 real with multiplicity 2. I might have missed one. But we know an awful lot. So, and we know that a fifth degree polynomial can either make 4 turns, 1, 2 turns, 3 turns, and 4 turns. It could make 3 turns. Oh, sorry, not 3 turns. It can make 2 turns. And maybe it just makes those 2 turns and keeps going. Maybe it makes those 2 turns and has a flat point. Maybe it makes those 2 turns and thinks about flattening out, but then just keeps on going. And many more. Any questions? All right. So this only seems like it's a lot to remember because it's a lot to remember. And some of it comes from previous classes that may and the information may or may not have been discussed. A lot of times we don't do deep dives into polynomials in our pre-calculus or algebra classes because there's so much else to worry about. Any questions? Comments? Deep thoughts?
Yes, Professor, just a quick one. On the last four draft, so we have 4 turns here. So we know that F prime will be 4 critical point, correct?
4 distinct real zeros.
Oh, critical point, okay.
Yeah.
And then on the second draft, there's a 2 turns, so we have 2 critical point, right? The max and the minimum.
Yes.
And then the third draft, we have, how many turns is this one?
There's only 2 turns, but there's 2 turns with a flat point.
So that would be 2 critical points.
No, there's 3 critical points. Places where the graph is flat are critical points.
Even it's 2 turns, it could have 3 critical points.
Yes.
Okay. Okay. And the last one will be 1 turn, 2 turns.
Two turns,
Mhm.
but no flat points.
So do we have critical point? We do, right? 2 or 3 in this one?
We have to have 2 critical points because that represents those 2
Right.
turns.
Okay. Thank you, Professor. Thanks.
All right. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.